first one we're going to go through is related to what I was showing you just a moment ago with the timing diagrams of L1 substates, and how would you actually make measurements of these timings using the setup Patrick just described. So some of the interesting things are, for example, the clock request being asserted to the reference clock being valid to the link entering L0. So these are events that we can see on the different instruments. But how do we measure timing between each of these? And that's where the setup is very convenient, because having time correlated, time synchronized, and cross triggering and probing between the events, we can easily measure these. So the first thing we have to do is set up the trigger, and we're going to use the protocol analyzer in this case to look for. We can just say look for the clock request being deasserted, the clock request being asserted. We're basically looking for the entry and the exit to the L1 state. We could use other things, like we could use the electrical idle ordered set or the PM enter L1 DLLP, but this is just a very straightforward way of doing it. So using the clock request line. So you can see on the right side of the screen here, this is the trigger setup on the protocol analyzer, and this is going to provide an external toggle trigger out to the oscilloscope, and it can do it multiple times as well. So we can take advantage of the sequence trigger in the protocol analyzer to send pulses to the oscilloscope to mark when we would capture these events on the oscilloscope. And CrossSync PHY has the advantage that we can look at multiple different segments within the oscilloscope trace. So what we're going to do with the oscilloscope is look at 4 distinct signals here. So we have a by 4 link on the protocol analyzer. So we're looking at everything striped for the data link layer and above, and then we can see the data link layer packets there, the EIOS, and then the link training is happening independently on each of the lanes because the order sets are down each of the lanes. So we're actually just going to look at one of those lanes on the oscilloscope, but we have the full capability of the multi-lane triggering on the protocol analyzer. So on the left side, we're looking at the clock request signal. We're looking at the upstream lane 0 of PCI Express, that's the pink one. Lane 0 downstream is going to be the downstream, the blue one here. And then we're also going to look at the reference clock. So this is something that's completely invisible to the protocol analyzer. But what it allows us to do is make a trigger between the protocol analyzer to look at the entry and exit of L1 and L1 substates. Then we can easily measure the clock request to refclk to L0 timings. So this just annotates the trigger condition happening on the protocol analyzer, the clock request being deasserted. So that's the entry to L1.2, and that can be correlated with what happens on the yellow trace on the oscilloscope here. So we can see the clock request signal toggling, and that relates to the part inside the blue box from the timing diagram up in the top right here. And then the next thing we see is the exit from L1. So that's where the clock request signal is asserted. So that's saying I want to start the wake up from L1. And these segments, these are 2 separate segments on the oscilloscope. So we didn't have to capture all that time in between those 2 events. So that could be a long time, but we used the trigger sequence on the protocol analyzer to be able to capture segments around those events. And then at the top of the screen here, we have the trace from the protocol analyzer, which is relatively long. And then the yellow parts are the segments that we captured on the oscilloscope around the times that we're interested in. The key here is that these traces are all time correlated with each other. So we can actually make measurements between the event on the protocol analyzer and the event on the oscilloscope. So we can also jump directly to the exit state. So if we navigate through the protocol analyzer, we can add markers here and then jump to the logical states on the protocol analyzer trace, and it will jump to those states in the oscilloscope trace. So this is very convenient for the analysis. So here's an example measurement from L1.0 refclk on timing. So this is the timing from the clock request being asserted, indicating the exit of L1.2. So moving from L1.2 idle to L1.2 exit until the point of the reference clock starting. So we're using the protocol analyzer for the trigger on clock request being asserted. And then in this case, we can observe the clock request line in yellow and the reference clock in green and make an accurate measurement using the cursors on the oscilloscope. And in this case, it was 301 microseconds. It's a very straightforward way to capture and analyze and make those measurements on the oscilloscope using the protocol analyzer as a tool to be able to get to those points very easily. The next measurement would be from the time where the reference clock is valid until the recovery is identified. So recovery is going to look like training sequences happening on the trace. So we can see the training sequences in the protocol analyzer trace. We can see the ref clock becoming valid time on the oscilloscope in the green trace here. And then we can also see exactly when the first training sequence happened on the oscilloscope. So again, we can use the triggering from the protocol analyzer and then use the time measurements on the oscilloscope. So the trigger takes us right to exactly the points of interest on the oscilloscope trace, and then we can use the cursors on the scope to measure that. So in this case, the measurement was 53 microseconds. And then the last measurement here is from valid reference clock time to the start of the L0. So we've got the mark here on the timing diagram, so we know exactly when that happened. We know when the reference clock started from the oscilloscope trace. And when did it reach L0 is something that we really can't see from the oscilloscope, because it's going to go from training sequences, it's going to send an SDS, and then the link is going to be an L0, but we can't really determine that time on the oscilloscope. So that's where on the protocol analyzer, we can search for the SDS, the start of data stream ordered set. That's going to give us the timestamp of when the link entered L0. So we can make an accurate measurement between ref clock valid to L0 using the two tools. Very, very powerful set of tools here. So then we can get the time from the SDS packet and compare it to the start ref clock. So in this case, it was 384 microseconds. So we can see that SDS on the protocol analyzer very easily. We can search for it even, something that's very hard to do from the analog side of the trace, but that allows us to make that measurement and navigate very easily.